All right, 1.3, congruent by coordinates. So this definitely involves some transformations, but a lot of it is review of our trigonometry unit, as you'll see. All right, so number one, calculate the length of each side in both these triangles. All right, well, these sides are pretty simple. 2, 3, 2, 3. Okay, and I see they're both right angles. So actually, I already know that these two triangles are congruent by SAS. So I only really need to do one. I don't need to do both. All right, so same thing we did in the do now, use the Pythagorean theorem. These are my legs, opposite my right angles, my hypotenuse, so this is my missing side I'm trying to find. All right, so I put out my formula first, a squared plus b squared equals c squared. Then I'm plugging in 2 squared plus 3 squared equals c squared. 4 plus 9 equals c squared. 13 equals c squared. And this, of course, is not the loveliest answer we could have gotten because, you know, C13 is not a perfect square, but it doesn't really matter. I'm just going to write, after I radical both sides, that C is equal to radical 13. All right. Why am I choosing not to put this in my calculator and write out the whole number? Well, radical 13 is an irrational number, which means it's a non-repeating, non-terminating decimal. It doesn't end, and it has no pattern. So I could never write this number out if I wanted to, so I'm just going to leave it as radical 13. All right, so I'm going to write radical 13 here, and I'm going to write radical 13 right here. All right, and I'm done with that. Okay, calculate the measure of each angle in triangles ABC and DEF. Well, again, since they're congruent, I only have to do it for one of them, and I know for both. I already know this angle is right just because of the way it's drawn with the grid lines. I can easily assume that that's a right angle. That would kind of be ridiculous if it wasn't. That's one of those assumptions you can just sort of make. But to calculate the other angles is going to be a callback to some trig. So the first thing I'm going to do is calculate this angle F, or angle EFD. But since there's only one angle at the vertex, I can call it angle F, no problem. I'm going to call it X, just to be a little bit easier to refer to. All right, so if we're trying to find an angle in a right triangle and we have the sides, that's called inverse trig. So because I have all three sides labeled, I could use any inverse trig function I want. I'll use sine. So sine, if we remember, is going to be opposite over hypotenuse. So if I look at x and I go to the side opposite it, I get 3. And the hypotenuse is radical 13. And what's different about inverse trig is that for inverse trig, you put the ratio in the function. Whatever your answer is going to equal the angle measure that you're looking for. So I'll show you how I do that now in my graphing calculator. All right, again, if you don't have a graphing calculator, I did send an email. TI is releasing free software during the coronavirus for an online graphing calculator. So if you have a computer, or I think they have a mobile version as well, you can get one for free there. If not, a scientific calculator has trig on it as well. All right, so if I want to use inverse trig, I'm going to press second first, and then I'm going to press sine to use inverse sine. I'm going to put my numerator in first, 3. A line in a fraction just means division. And then I'm going to put radical 13. All right, and to get the radical, you press second, x squared. All right, you see that little blue radical right above the x squared? That's what we're looking for here. And I'm going to close my parentheses completely, and I press enter. Oh, one thing I forgot to do. Make sure you go to mode, and look at that. I am not in degree mode. And I was able to tell I made a mistake right away because I was like, how could that angle be 0.98 degrees? That doesn't make any sense. So let's try that again. That looks a little more realistic. All right, they don't tell me what to round to, which is a little bit annoying, but I'm just going to round to the 10th place. So that's equal to 56.3. All right, good. So if F is 56.3, that would also mean that C right here is 56.3, since they are corresponding angles in congruent triangles. All right, that would be CPCTC, telling me that corresponding parts of congruent triangles are congruent. Okay, great. Now let's find the missing angle. So, I mean, I could use inverse trig again, or I could just know that the two acute angles in a right triangle are always complementary. That means they add up to 90. So I know x plus y equals 90, or substituting 56.3 in for x, I now have a single variable equation that I can easily solve. Getting y alone, I'll do that quickly in my calculator. We get y is equal to 33.69006, which is about 33.7. All right, so I'll write that here. All right, that's good. All right, the triangles are congruent. How do you know this is true? Side angle side, congruence, postulate. All right, and really, if you wanted to, you could have used ASA, HL, AAS, side, side, side. You could have literally used any of the congruence postulates. So there are 5 different correct answers for number 3. But that's the one I used originally, so I'm going to stick with that. All right, because the triangles are congruent, there must be a sequence of rigid motions that takes one to the other. Find a sequence of rigid motions that takes triangle ABC to triangle DEF. So they've told me, by listing it this way, that A corresponds to D, B corresponds to E, and C corresponds to F. So the easiest thing for me to do would be to immediately try and map try and map A to D, because they want us to take A, B, C to D, E, F. So if I want to bring A all the way over to D, the easiest way to do that is a translation. So I would be going down 1, and I'd be going over 1, 2, 3, 4, 5. So that would be -5, since we're going towards the negative side. So my first rigid motion would be a translation of -5, comma -1. And what I'm going to do real quick is I'm going to redraw this triangle now so I can see what my next plan of action would be. So I'm going to put A, B is 3 units away, so B would be right there. C is 2 units up. Yeah, that looks good. Great. So now I can see that I also want to take B to E, and looking at the line segment that AB and DE make, I can see, let me move it down. I can see that that's 90 degrees. So that would just be a rotation counterclockwise of 90 degrees. So that would be my next. Then rotate 90 degrees. And anytime you have a rotation, you always want to state what the center is. So I'm going to say centered at, since A is already mapped to D, I don't want to move it at all. So I'm going to say centered at -3, 0. That's where I want my center of rotation to be, so A stays exactly where it is. All right. I don't know. I'm sure there's another one. Oh yeah, are you ready for more? What single transformation would take triangle ABC to triangle DEF? Well, if I look at this, maybe I should not draw in pen. Now it's all getting all messy. Whatever. Just to check the orientation though, if I go around like this, ABC, reading it in alphabetical order, or the order that the triangle is supposed to be, ABC, I notice that that's in the counterclockwise direction. And if I do DEF, that's also in the counterclockwise direction. So I know for a fact it can't be a reflection, because if you remember, reflections do not preserve orientation. If I were to reflect triangle ABC over this line like this, I would have C prime, A prime, B prime. ABC is clockwise. Now ABC is counterclockwise. So I know it's definitely not a reflection. I can't do it in a single translation because it's just, they're sort of tilted or turned. So I would have to do some sort of rotation as well. So what I have to do is I have to find a single point that is equidistant from DA, EB, and CF all at the same time. All right, and that is actually a rather complex construction, but I will show that. I don't expect any of you to be able to do this on a test, but it is pretty cool. Actually, I enjoy doing it. So the first thing I'm going to do is I'm going to make a line segment connecting D and A. a line segment connecting E and B, and a line segment connecting C and F. All right. So C and F are collinear with E also. Okay. So what you want to do to find out where the center of rotation is you want to make a perpendicular bisector for all three of these lines. Why do I want to make a perpendicular bisector? Well, I'll explain that in a second. First, we want a point for for our center of rotation. Okay, my lamp is falling over. Just had enough math for today. My center of rotation has to be equidistant, right? So the most obvious equidistant point is going to be the midpoint of this line. So actually the easiest, yeah, I'll do the construction. All right, so let me find the midpoint of this line segment right here. So I'm going a little more than halfway. Do that from both sides. All right, I'm going to make that perpendicular bisector. So what's very interesting about this perpendicular bisector is that, wait. All right, I don't know, this is sort of an odd question for them to ask because it's going to be very difficult to actually locate the point. It looks like it's actually off the grid. Any point on this perpendicular line is going to be equidistant from A and equidistant from, equidistant from D and equidistant from A. No matter where I go on this line, I am always the same distance from those 2 points. So that's what we want for a center of rotation, equidistance. I also know that much more simply, if I look at C and F, one's at 5, one's at -5. So I know that if I want a perpendicular line between these two, that's going to be this y-axis because they're both equidistant from that y-axis. So why did Mr. Burnett kind of laugh and say, why would they ask a question like this? Well, look where these two lines intersect. That's like totally off the grid. It's like probably -3, 0. So I don't know why they would ask. That's a ridiculous kind of question to ask, in my opinion. I guess it is a challenge. Are you ready for more? But I don't know why they would make it so difficult. It looks like it's that. I'm going to double check, and I'm going to do one last perpendicular bisector for between B and E just to make sure. Because it's possible I made some mistake. Looks like I'm probably right. So connect that perpendicular bisector, and where all three perpendicular bisectors connect, that's going to be my center of rotation. And looks like I'm right. So that looks like it's about -3, 0. All right, now I want to see how many degrees that is. So yeah, there's layers to this, I can tell you that. All right, let's see. If I make a circle connecting C with F, I don't know what they were thinking designing this problem. All right. Now to see how many degrees, this is ridiculous, oh my God. I'm gonna connect it. I hope this doesn't scare any of you away from math or freak you out, because nothing I ever assign will be like this. And I can already tell it looks like it's gonna be 90 degrees clockwise, but let me just do another perpendicular bisector to make sure. Okay, so this would be like the above, like a challenge question. Let's see. I'm gonna assume that's pretty accurate. It looks like I'm a little bit off, maybe by like a centimeter, but we'll chalk that one up to human error. All right. So yeah, that looks like it would be a rotation of 90 degrees, centered at -3, 0. Oh, I'm sorry, 0, -3, because x comes before y in the alphabet. All right, hopefully that didn't scare too many of you away from math. If you did follow along, awesome. It's very, very impressive. I am beyond impressed. All right, enjoy the rest of your day.